Dear professors, please turn off your microphone and camera. Participants, please don't present your screen in between. Hello? Sir, join. Good morning, professors. Today I'm really grateful that we are going for the day 5 of the program. I welcome Professor Sina Posal, Professor Agbula, and all the other dignitary faculties for this 7 days FDP program. Now we'll start the program shortly as Professor Raghavan is trying to get in. We'll start the program shortly. Please, professors, please turn off your microphone and camera off and don't present your screen in between. Mohan Rao sir, please turn off your camera off. Mohan Rao sir, please turn off your camera. We'll start the program shortly. Yeah, Professor Raghavan sir came. I think we can start the program now. Geeta ma'am, can you hear me?
Yes, Parimala, we can start it.
Yeah, thank you, ma'am.
Okay, fine. Good morning, dear participants. Today we are into the 5th day of our International Faculty Development Program on Avant-garde Trends in Mathematics. And it is a very pleasure to see you all, even the Sunday, you all attend this international FDP, which means that it shows all our enthusiasm and interest towards the knowledge of sharing and getting new things into our mind. So now today's resource person, we have Professor Raghavan, and he had his MS degree, which is an integrated 5 years degree in physics, IIT Delhi, in the year 1985. And he got his doctoral degree in mathematics at Purdue University, 1991. And he has got his first employment as a research visiting assistant professor in Michigan State University during the year 1991 to 93. And then he was into the faculty at Chennai Mathematical Institute, 1993 to 2001. And currently, he is a faculty at the Institute of Mathematical Sciences since 2001. And he has got recognitions like he has elected as a fellow of the Indian Academy of Sciences during the year 2011. And also he has been elected fellow of the National Academy of Sciences 2016. And may I request the Professor Raghavan from Institute of Mathematical Sciences, CIT Campus Tharamani, Chennai, to take over the platform and share his valuable inputs to all participants. And sir, it's my great pleasure in inviting you for this International Faculty Development Program. Even on Sunday, you don't mind and you spend your valuable time with us. Thank you so much, sir.
Good morning and thank you for that introduction. Am I audible?
Yes, sir, you are audible, sir.
Okay. So I will start now. And I will share my slides, and I have sent them already. So you feel free to share the slides with the PDF file of the slides with the participants. And I had, along with the abstract, sent a link to the notes. So I hope the participants have that link. If not, I can send that link again. And did everyone get the link? Was the link shared with the participants?
So
it was along with the app.
Sir, please share it now. I have not shared it.
Okay. Sure. Do share that link of notes. That's useful. Yeah. So maybe I should start. Should we start now? Should I start presenting? Hello?
Yeah, sir, you can start, sir.
Yeah, okay.
We are
I'll
audible
start
on this
presenting. I'll start presenting. Okay.
Yeah.
It'll just take me half a minute. Please bear with me. Okay, can you see this, all of you?
Yes, sir, you have shared your screen.
Okay, good. I start now, but at any moment, you are welcome to stop me and ask questions. And if something is not
Sure,
clear,
sir.
yeah. And I would request feedback because I am since I cannot see your faces, it is not clear to me whether I am making sense or not. So I will ask for vocal feedback. And when I ask for it, please do unmute your mics and give me feedback, or better still, or say that you understood it, or better still, ask questions. Okay? So with that, should we go ahead? The title of the talk is The Line of Best Fit, a Linear Algebraic Approach. So what do we mean by the line of best fit? So in this picture that you see, I have drawn, okay, one second. Let me try to make it full screen so that that is better. Okay, is this better? It's full screen now. Yeah, is this okay?
It is clearly visible, sir.
Very good, thank you. I will, okay. So what you see here is something that we do from high school, right? So you have the x-axis and the y-axis. And what I have is a set of data points. So what do we mean by data points? These could be data that is generated in an experiment. Say you have, for example, on the x-axis, some, it could be counting time in the number of days, say starting in March or something of this year. And on the y-axis, you could have logarithm of the number of COVID infected patients, number of total cases counting up to that day. And if you do this, then you expect to see a straight line in certain regions. This is what we mean by the infection is spreading exponentially, right? Because I'm plotting on the x-axis the time in days, and on the y-axis not the number but the logarithm of the number of total infected patients. If I do that, then and plot, I'll get some kind of some number of points, and in certain regions, when for example, when the infection is growing exponentially, what we call exponentially, then you expect to see a straight line. The points will approximately lie on a line, and what you would like to do is ask the question, which is the straight line that best fits this data? Okay, is the question clear? So you have a set of data points. This COVID example was just an example. If you didn't follow it, that doesn't matter. The mathematical problem for us is you have a set of data points, and you, for some physical reason or for some reason of applications or some reason that comes from outside of mathematics, so to speak, you expect that these lines should lie on a straight line. And then the question you ask is, what is the line that best fits this data? Is the question clear to everybody?
Very clear, sir.
Okay, good. And if at any point, if something is not clear, please don't hesitate. You may unmute your mics and ask me a question anytime. Okay. So in the bottom of this screen here, I have written 3 questions. What does it mean for a line to best fit the data? We are saying intuitively that there is a line which best fits the data. But what do we mean by best fitting the data? This is something that we have to nail down. We have to make precise. This is, see, in mathematics, when you are modeling an application, you have something and in the real world, and what you are trying to do is model it mathematically. So you create a mathematical model, and in doing so, you have all these, you have some vague notions of what you want and what is desirable, what is not desirable, and you have to use this vague language before, when you start before the mathematical problem becomes well defined and precise. So when we ask this question, what does it mean for a line to best fit the data? This is precisely what we are doing. We have some vague notion, some intuitive notion that there must be a line that best fits this data. And then we ask ourselves, what does it mean? How can I mathematically make this precise? And moreover, two other questions come up immediately. Why should such a line exist? I mean, it is not clear at all a priori. A priori meaning before we think about it and really answer, such a line may not exist. So the question is, why does such a line exist? And furthermore, why shouldn't two different lines both fit the data in the best way? Maybe one line does by some criterion or criteria, it is the best fit. Some other line may also be the best fit by the same criteria or a different set of criteria. So what are the criteria, and does there exist a line or perhaps many lines? And those are the kind of questions we will pose and answer. Is this clear? So I repeat, to summarize, you're given a set of data points, and the question is, how do I fit a straight line through this data in the best possible way? This is the question. Now, of course, we have to understand and answer, what does it mean for this straight line to best fit the data? We also have to understand, maybe is there a single line, maybe there are multiple lines, or maybe there is no line, right? So these are the questions. So it is, what do we mean, and whether the line exists and whether it is unique. In other words, what do we mean, and then existence and uniqueness, as we call in mathematics. Okay, is this clear? So should we go on?
Multiple lines possible, sir?
A priori, for right now, we are leaving open that option. It may be. So it means it depends on what we mean by the best line, right? See, so look at this question on the first line. What does it mean for a line to best fit the data? We have to give meaning to this statement or phrase. Do you understand? That is part of the problem.
Yes, sir. Yes, sir. Okay.
And depending on what meaning you give it, right, your answer may vary. And the meaning that we will make it, I hope to give it meaning, and I hope to convince you that the meaning that I'm going to give is a very reasonable meaning. Okay.
Yes, sir.
And with that meaning, it will turn out that there is only one line. Just to look ahead.
Yes.
Okay. So multiple lines are not possible given the meaning that we will attach to it.
Yes, sir. Yes, sir.
Okay. But,
okay, sir. Thanks.
Yeah, good. Any other questions? Good. Thank you for the question. Any other questions? Okay. If not, we'll proceed. But I repeat, I will never tire of repeating. You can please interrupt and ask questions at any point. Okay. So let us look at this very simple example. Okay. I call this the running example because I'll come back time and again to this example. So you are given 3 points here. 1, 1, 2, 3, and 3, 3, right? So I've plotted 1, 1. This is x-axis. Along the x-axis, it is 1, and along the y-axis, it is 1. And here it is 2, 3. So along the x-axis, it's 2, and along the y-axis, it's 3. And here it is 3, 3. So it's along the x-axis, it's 3. Along the y-axis, is also 3. Right? I'm given 3 points. Right? The question is, which straight line best fits these 3 points? Of course, these 3 points do not lie on any line. That is obvious, right? If I draw a straight line, then there is no straight line which contains all the 3 points. Right? If there was, then we would be done. That would be the line of best fit, intuitively at least. Right? But there is no line that passes through all these 3 points. So our problem is, should I draw it? Are you able to see the cursor on my screen?
Yes, sir. Yes, sir. Yes, sir.
So I'm trying to point with my cursor. I hope you can see it. So maybe I can draw the line like this, or maybe I can draw the line like this. Maybe I can draw the line like this. It is not clear right now. Which of these, how am I going to draw the line? We have to think about it and come up with a criteria, and then go ahead and find, based on that criteria, what that line is. Is this clear?
Yes, sir. Very clear, sir.
Okay. So we are going to, at the end of the talk, I will tell you how to solve this particular problem. So it is very important in mathematics that we have a paper and pencil and work things out as we go along. I find that just listening to mathematics talks, like watching a movie, with our hands free, doesn't always work. So there is a lot of time is going to be there in my talk. So I have only about 8 slides or 9 slides. Okay, so I'm going slow in order that you can take notes, you can think about it, you can ask questions and follow what I'm saying. Okay, so my suggestion to all the participants is to draw this picture on a sheet of paper, take these 3 points and think about how are we going to solve this problem. Okay, with this, should we go ahead?
Yes, sir. We can proceed, sir.
Okay. Okay. So let us, here is in this picture, I've drawn these several points, right? So in the previous example, this is what is called a toy example, right? When you do an experiment, you usually don't have just 3 points. You have hundreds of points, maybe even millions of points, right? Depending on the experiment. It is usually not a small number of points. But this is what is called a toy example, in the sense that it's a simple example which we can do by hand, and that will illustrate the principles, and we can, once the principles are understood, we can go ahead and apply them in a larger example with hundreds of points or even millions of points. So while this is not a typical example that you're likely to come across in any experiment, it nevertheless illustrates all the features of the problem. So this is a good thing to have. We often do that in mathematics. When we are faced with a problem, we try to come up with toy examples, simple examples, which may not, the actual physical problems may be much more complicated, but nevertheless, we try to simplify and look at toy examples so that we can understand those examples. And once those examples are understood, then we can graduate and go ahead and try the more complicated physical examples, right? Okay. Now, here I have depicted, try to depict a more typical physical example. So there are many points here: x1, y1, x2, y2, x3, y3, x4, y4, xn, yn. I've called them x1, y1 on the top of the screen here, x1, y1, x2, y2, xn, yn. Some n points are there, right? And the question, so I've drawn the x-axis and the y-axis. And I have, okay, let's say this line, I draw a straight line. And as we know, one of the forms of the equation of a straight line is y is equal to mx plus c, right? We have learned that in high school. Y is equal to mx plus c. What do m and c mean here? C represents what is called the y-intercept. That is here, I've drawn it here. The distance of from the origin to the point where the line intersects the y-axis. Of course, in this picture, the line intersects the y-axis on the positive side. So C is positive for the line drawn in this picture. If it's going to intersect the y-axis on the negative side of the y-axis, then C would be negative. right? Okay, C is called the y-intercept. And what is M? M is called the slope. It is the tangent of this angle that I've drawn here, theta. That theta is the angle that the straight line y is equal to mx plus c makes with the x-axis, right? Wherever it meets the x-axis. So this line I have drawn here is parallel to the x-axis. Therefore, this angle is theta, and the tangent of this angle, in other words, it is this delta y by delta x, right? If I go along this line, for every the question is how much is the change in y for unit change in x? That is the meaning of slope, and I have it here. Tan theta is equal to delta y by delta x equal to slope. Okay, so this is a review of very basic high school algebra of what we mean by a line. Y is equal to mx plus c, and what do m and c mean? Now, what is our problem? Given a set of these points, x1, y1, x2, y2, x3, y3, x4, y4, we have to find just two constants, m and c, right? To find a line means to find m and c. If I know m and c, then I know the line, right? So the problem is to find, as written on the bottom of the screen here, we need to find m and c. So going back one slide, looking at this problem, what do we have to do here? I have to find m and c. Given 1, 1, 2, 3, and 3, 3, this is the data given to me. I have to find m and c subject to the condition that m and c, the line y equal to mx plus c, best fits. So I must find m and c subject to the condition that this line somehow best fits the given data points. This is clear? We still have to define what it means for the line to best fit the data points. We have not come to that crucial point yet. We will come to it very soon, but we have not come to it yet. So far, is everything clear? Are there any questions before we go on?
No, sir.
Is everything clear?
Yes, sir. It is
Okay.
clear.
It is clear. So should I go on?
Yes, sir.
Okay. I repeat, I appreciate, see, if I was standing in front of you and giving this lecture, it would be very different, because then I can judge by seeing your faces whether you're following or not. Now I don't have any such feedback. So sorry for repeatedly asking you for feedback, but I feel very frustrated if I'm saying something and not being understood. So I'll repeatedly keep asking you for feedback. Do give that to me. And I would appreciate if you ask me questions, then or clarification. It doesn't have to be a question. If you've understood something and if you want to verify whether that understanding is correct or not, that's a very good thing to do, because maybe others have the same question too. So I would really appreciate a detailed feedback. If you ask me questions, I'll be most happy. Okay, so I'll proceed, but feel free, I repeat, to interrupt and ask questions or ask for clarifications or even make remarks. Okay. Okay, now we slowly come to, we are going to try to understand what it means for a line to best fit the given data. Okay, so imagine for a moment that all data points actually lie on a single straight line. Okay, suppose for a minute that is true. That's not going to be true. It's not even true in our simple example here, right? But nevertheless, for the sake of argument, let's imagine that all of them lie on a single line. Then, so what will you have? So there is some line y is equal to mx plus c. And what does it mean for the point x1, y1 to lie on that line? It means when I plug in y1 for y and x1 for x, the equation is satisfied. That's what it means for x1 comma y1 to lie on the line y is equal to mx plus c. So here y1 is equal to mx plus 1 c, mx x1 plus c means the first point, the x1 comma y1 lies on the line. The second equation similarly means x2 comma y2 lies on the line, and so on. So since I'm assuming just for the moment that all the n points lie on this line, so I have these equations. y1 is equal to mx1 plus c, y2 is equal to mx2 plus c, yn is equal to mxn plus c, right? So I have all these equations, n equations on the left side here, and I can now, instead of writing it in this form, I can write it as a matrix equation, like so. I have y1, y2, y3, yn. Okay, I write that as a matrix, as a column matrix, n cross 1 column matrix. Okay, these are knowns because I know the value of y1, y2, y3, y4, yn because those points are given to me. Okay. And on the right side, I can write this using the standard matrix multiplication. I can take this m and c, and those are my unknowns. Those are what I need to find. And I have this x1, x2, x3, xn, and they, if I write them as this column here and 1, 1, 1 here, and you see if I do matrix multiplication, I precisely get x1 into m plus c, 1 into c, which is c. So the if I equate the first entry here y1 equal to the first entry that I get when I multiply these two matrices, I get precisely mx1 plus c, mx2 plus c, mxn plus c, and so on. Those are the entries here. So I hope it is clear using just simple matrix multiplication that this matrix equation on the right side is nothing more, nothing less than this system of n equations here. What we have done, therefore, is just converted this system of n equations to this single matrix equation. Okay. Also, just observe that there is a slight change of notation here from the usual notation. Usually we have x and y as unknowns, but here in my notations, sorry for that, but this notation seems to be most suited to the problem at hand. So x1, x2, xn, and y1, y2, yn are all known because those are the x1, x2, xn are the coordinates of the x coordinates of the points that I'm given. y1, y2, yn are the y coordinates of the point that I'm given. N is the number of points that I have. M and c is what I have to find. So going back here, in this problem, n would be 3, and x1, x2, x3 would be 1, 2, 3. y1, y2, y3 would be 1, 3, and 3. 1, 3, and 3 for y1, y2, y3. And so if I plug that here, I would have 1, 3, 3 for y1, y2, yn, and x1, x2, xn, I would have 1, 2, 3, and 1, 1, 1. Here MC, those are the unknowns I have to find. And we would solve the system of linear equations. I have n equations for the two unknowns m and c, and then we would be done. Okay, so let's see. Maybe I'll show you right here. Okay, so if all these 3 points that I have, if they did lie on a line, I would be able to solve this equation. What I would have is I'm trying to solve this equation. Here, look, y1, y2, y3, x1, x2, x3. This is 1, 1, 1, and MC. What I have to do is I have to solve this system of equations. That's what I have to do to find m and c, right? I would be able to solve it if all of them lie on a line. But if they do not all lie on a line, then I'm not able to solve that equation. Anyway, we'll come to that in a minute. Let's come back here. So this is the case when all of them lie on a line. I would get a system like this, of equations like this. I would try to solve it for m and c, and solving that system of equations, I would be able to find m and c. Is this clear?
Yes, sir, it is clear.
It is clear?
We understood.
Okay.
Yes, sir, it is clear.
Okay. In fact, as you observe,
Yes, sir.
Very good. Thank you. Thank you for the multiple feedback. In fact, you don't need any equations because there are just two unknowns. You would be able to solve it with just two equations, right? If I had two independent equations, I would be able to solve for M and C, right? This just corresponds to the fact that this is remember, I'm talking about the case when all the points lie on a line. If I give you just 2 points, 2 distinct points, then the straight line is determined already, right? So this means that just having 2 of these equations corresponding to points that are distinct would have enabled me to find M and C. I have more equations here, but doesn't matter. Even if I had more equations, just having 2 independent equations would have been enough for me to find M and C. Okay, so I will proceed now. But once again, I repeat, do stop and ask questions if things are not clear. Okay, now, but that is our problem. The points do not all lie on a straight line, right? If they did lie on a straight line, then I would solve the system of equations and be done with it. Now, but the points do not all lie on a straight line. They are not expected to do so in most cases. Okay, then what do we do, right? That is our problem. If you go back to our simple problem here, these 3 points do not lie on a line, right? So what do I do? What the answer is, I nevertheless do the same thing. That is, I write the system of equations, right? So just imagine what I expect. I expect all of them to lie on a line, M and C. So I write the equation y1 is equal to mx1 plus, okay, this is the same set of equations. Y1 is equal to mx1 plus c, y2 is equal to mx2 plus c, yn is equal to mxn plus c, and I convert it into a matrix equation, and that's what I have here. Okay. The only problem now is this does not have a solution. Is this clear? So you can still write this system of equations, but now this does not have a solution. So the question that arises is there a best approximation? I'm using some technical terms here, I'll explain these, to an overdetermined system of linear equations as above. Okay. So what do we mean by overdetermined? So as you know, I'm given here, how many unknowns do I have? There are only 2 unknowns, M and C. Okay, and how many constraints do I have, so to speak? A constraint is a condition. So there are n equations. Y1 is equal to mx1 plus c means that I am putting one constraint on M and C. M and C must satisfy this constraint, y1 is equal to mx1 plus c. I must also have y2 is equal to mx2 plus c, which means that's a second constraint on M and C, and so on and so forth until yn is equal to mxn plus c. That is yet another, there are n different constraints on M and C. So I have 2 unknowns, but I have n constraints. Such a thing is called, where n is a large number. Usually, typically, as we said, in an experiment, it may be 100 or 1,000,000 or something like that. In our baby example, remember, there are 3 points, so there are 3 constraints, okay? And they are inconsistent. What this means is precisely that the given points do not lie on a line, right? Do not all lie on a line. So they are inconsistent. So I have an overdetermined, so that's what is meant by an overdetermined system. I have few unknowns, lots of equations, and there are too many constraints. These equations represent too many constraints. There is no, I cannot, if I look for an exact solution, that does not exist. So here you cannot solve for M and C. Okay, that is the problem. So you can formulate it this way, but then I have to think about the following question. And this is, okay, I am given a system of equations. I am unable to solve it. But I want to answer my question, original question, right? Is there a line of best fit? So I must somehow find a way of solving a system which does not have a solution. That seems like a contradiction, right? I must find a way of solving a system that does not have a solution. So what do? We must somehow modify this system in some minimal way, right? And that is the key, in some minimal way, because I don't want to see, because this system here represents my physical reality. Now, in the physical reality, there is no line passing through the points, okay? Which precisely means that I cannot solve the system for M and C. But then what do I want to do? I am not asking for, I mean, I can see that there is no line passing through the points. So what is the next best thing I can ask for? I ask, how can I find a line that best fits this data? Right? That is the question we started with. So what are we going to do? How is that question going to be modified here? That question is going to be transformed here as follows. How am I going to modify this system of equations ever so slightly, so when I modify slightly, what I'm doing is I'm trying to keep very close to the physical set of points that I'm given, but I'm going to modify in such a way that this system has a solution, which means once it has a solution, I can find the M and C, and the value of that M and C will be my line of best fit. I hope, have I made myself clear? This is the key point here. I hope this is clear. If not, I can explain again. And let's pause here for a couple of minutes, and I'll wait for questions or comments. And then once things are clear, we'll go forward.
Very clear, sir. We understood.
Okay. Okay. Anybody else? Any questions, or is this clear?
Clear, sir. Proceed.
Okay. So should we
Sir,
go ahead?
can you explain one more time?
Sure.
Sir, excuse me, sir.
Yes.
One of the participants have asked that what's the difference between the linear equation and Diophantine equation?
Linear equation and?
Diophantine equation.
Okay. So Diophantine equation usually refers to an equation with integer entries, right? So when we try to solve, given an equation like say x square plus y square, just to give this famous equation, x square plus y square is equal to z square, right? For example, this is if x and y form the sides of a right triangle, the lengths of the sides of a right triangle, and z is the hypotenuse, then you have this Pythagoras theorem, x square plus y square equal to z square, just to give an example of an equation. And if I try to solve this, for example, 3 square plus 4 square is equal to 5 square. So 3, 4, 5 is a solution for this. So this is, so what we try to do in Diophantine equations, the meaning is the equations to have integer entries, integer coefficients, and we try to find integer solutions, maybe even positive integer solutions. Okay.
Sir, excuse me, sir. Sir,
Sure.
Excuse me, sir. One of the participants have shared their screen, sir. So better
Okay.
you just once again share your screen so that screen will go down.
Oh, okay. I stop sharing and then start sharing.
Yes, sir.
Okay. I stopped sharing. Okay. Let's see.
Dear participants, please do not share your screen in between the presentation is going on.
Let me see if I should I. I'm going to start sharing again.
Yes, sir.
Okay. Is this good?
Yes, now it has been presented.
Okay. So let me go to full view presentation mode. Okay.
Okay, sir. Okay, sir.
And then go back one slide. Okay. So coming back to the question, Diophantine. So Diophantine equations are something to do with integer solutions or even positive integer solutions. Okay. So those are not relevant for us at the moment. You can forget about those for the purposes of this talk, right? When we mean a linear equation, so if I have an equation whose graph, so if I have an equation like y is equal to 5x squared plus 3x plus 7, I can draw the graph of this, right? I can take different values of x and compute the values of y, and then I can plot, right? And what I see is a parabola. The shape. So when you plot an equation, when you draw the graph of an equation, it has a shape. And what we mean by a linear equation is when the equation, if you draw the graph, it is a straight line, right? And then it is of the form, as we have seen, y is equal to mx plus c, or more generally, it could be of the form ax plus by plus c is equal to 0, where a and not both a and b are 0 to be. So the word linear refers to the fact that the graph of the equation is a straight line. I hope I have answered that question. You can forget about Diophantine equations for the purposes of this talk. They are not relevant for this talk.
Okay, sir.
Okay. Okay. So
Yes.
somebody was asking me, can you please explain one more time? Could that person please ask once again? They wanted something explained again. I'm happy to do that. There was a question just before this Diophantine equation versus linear equation question came up. I heard a voice from some participant.
Sir, just now you explained if the points are on the line, you just explained the procedure.
Yeah.
Now, if the points are not on the line, what we are going to do, you are explaining.
I'm going.
So that is I'm asking.
Okay. Yes, I'm going to explain. Okay. So I hope the following is clear. If the points do not lie on a line, then this equation does not have a solution. This system of equations that you see here. So let us go to the example. Just let's one more slide, and hopefully that will be clear. So let's look at our running example, right? Which means that we have this example here, and we are trying to solve this. We are trying to find the line that best fits these 3 points, right? Is this clear? This is the problem that we are trying to solve. And here, what I try to do is I write 1 is equal. So let's assume that there is a line, call it y is equal to mx plus c, and that on which all these 3 points lie. What are the 3 points? 1, 1, 2, 3, and 3, 3. So I have y1 is equal to mx1 plus c, y2 is equal to mx2 plus c, y3 is equal to mx3 plus c, and I have written those equations here, right? Because x1, x2, x3 are 1, 2, 3, y1, y2, y3 are precisely 1, 3, and 3. I hope this is clear, these 3 equations, and therefore, once I transform them into matrix form, I get this equation on the right side. Okay, and the point is, and look at the bottom here, what is written at the bottom of the screen here. This does not have a solution. Okay, this does not have a, never mind this because I'll come to that in a minute. This does not have a solution. Okay, which represents the fact that the 3 points do not lie on a line. So the question now becomes, they do not lie on a line, and therefore this does not have a solution. Therefore, how do I go about it? Now I'm stuck. I have a problem on hand. How am I going to come out of this problem? Right? That is what we are going to understand now. Okay. We have not done it. We are going to do it now. Okay, is this clear? I can explain again if you want.
Yes, sir.
Yes, sir. Yes, sir. It is clear, sir.
It is clear. Okay. Now let us come to the second part of this, because, starting with the because. Okay, now we are going to do linear algebra. As I said in the abstract, which I request the organizers to share with all the participants. So this problem of trying to find the line of best fit, we are going to look at it from the point of view of linear algebra. There are other points of view from which you can look at this problem, but today we are going to look at this from the point of view of linear algebra. So that is why I have formulated this as a system of linear equations, right? There are two unknowns, M and C. You have this system here, and I want to solve it, and I understand that there is no solution. Okay. Now, let us see, and this is the intuitive idea. If I'm given a system, I don't have a solution, and the idea is, I repeat, here this is the main idea, is how do I change the system? How do I change these numbers here, 1, 3, 3, 1, 2, 3, 1, 1, 1? These numbers here, maybe some of them perhaps. In fact, we are going to change this 1, 3, 3 as it turns out, as you will see. Okay, in some way, not too much, because I should not disturb it too much, because remember that this equation represents the reality of those 3 points that are given to me, right? So I must stay close to that reality, which means I must change it ever so slightly, as minimally as possible, as little as possible. Okay. However, after I change it, I must make sure that the system has a solution. This is the idea. So let us now think about this system here does not have a solution, and how am I going to change it so that it does have a solution? Okay, change it in some very minimal way, some naturally minimal way, so that it starts to have a solution. That is the question. Okay, and towards that, so this is the most important point to understand. I hope I have made this clear. I will stop here and again ask you all whether this point is clear.
Clear, sir. Very clear.
Very clear. Okay. So now let us understand why this system does not have a solution. Okay. So, for example, here I have written, if you write the right-hand side of this, you see when you do this matrix multiplication, you will get this 1 gets multiplied, this 1, 2, 3 in the first column here, those get multiplied by M, this 1, 1, 1 gets multiplied by C. So the right side of this equation I can also write as 1, 2, 3 into M plus 1, 1, 1 into C. That's what I've written here at the bottom of the screen here, right-hand side bottom of the screen, right? So this not equal to means this is, I'm not able to solve this. What does it mean? I am not able to find M and C. No matter what values of M and C I put, I will never be able to get 1, 3, 3 as a linear combination. I'm now using a word from linear algebra because this is a linear combination, right? I have M times this number, this vector plus C times this vector. Usually you write this M in the front and C in front, but never mind that. That is just a matter of writing. So 1, 3, 3 cannot be written as a linear combination of 1, 2, 3 and 1, 1, 1, which means no matter what values of M and C I choose, I will never be able to satisfy this equation. That's what it means to say I have this inequality here. So what does this mean? Looking at it geometrically, now we are beginning to move towards the solution. What we are saying is, look at so these are two vectors in real 3 space, 1, 2, 3 and 1, 1, 1, right? So these are two real vectors, and those two vectors span a 2-dimensional space inside real 3 space. Inside the real 3 space, they span a 2-dimensional space. And as I vary M and C, as I vary different values of M and C, I get all the vectors. The right-hand side varies over all the vectors in that subspace, in that 2-dimensional subspace. To say that this equation does not have a solution means precisely this vector 1, 3, 3 does not lie in that 2-dimensional subspace. Okay, so I have depicted this in terms of a picture. I'll just rotate this. Sorry for this. Okay, so that's a picture where I have. Okay. Here, I have drawn here 1, 2, 3, and 1, 1, 1. These are the 2 vectors here, 1, 2, 3, and 1, 1, 1. And this plane P here, I'm afraid this is not a very good picture. You have to imagine this. This P here that I'm showing here is the 2-dimensional space or 2-dimensional plane in 3 space, which is spanned by these 2 vectors, 1, 1, 1, and 1, 2, 3, not lie on P. Okay, so this is a bit okay. What I'll do now is I'll stop sharing, and then I will try to do some show with my hands something so that you can get a better understanding, and then we'll come back to this. Okay. Okay, I hope all of you are able to see me now. Am I visible?
Yes, sir.
Okay.
Yes, sir.
So you see, I'll show with my hands now because that's the best I can do. So you have this 2-dimensional plane here, right? Some 2-dimensional vector here, 1, 3, 3, which lies outside that plane. So this, my right hand is the, I'm showing the plane here with this hand, and with this hand I'm showing the vector. My forefinger shows the vector 1, 3, 3, which is outside that plane, right? This is the problem. Now we have identified the problem of why this system does not have a solution, because this vector here does not lie on this plane. So how am I going to remedy this problem? So it seems very natural by looking at this picture that I have here that I must somehow replace this vector by some point that lies on this plane, right? Right, that is the remedy that I have to do. I have to replace this vector by some point that lies on this plane. But then I must not change the point too much. I must change it minimally so that it comes into the plane. What is the best way to do it? Well, it's obvious that there is a point on the plane that lies closest to this vector, right? To the tip of this vector that lies closest to that vector, and it is that point that on the plane that I should choose. So is this explanation sort of, can you imagine this in your heads? And sorry, I am not able to. If I was standing in front of you, I would be able to do this better, but given this constraint of these technology, I'm not able to do that very well. So is this, does this make sense?
We could
Yes, sir.
imagine that.
But accuracy may be missing, sir. Accuracy may be missing.
So see, what we are going to do is we are going to this point that you have, this 1, 3, 3 in this example that we have, right? This vector is, so this one, these two vectors that I have, this 1, 2, 3, and 1, 1, 1. So let me go back and show you the picture once again. Okay, let's come back to the picture. Yeah, there it is. Okay, no, I'm afraid this is not very well drawn. I wish I could shade and show you the three-dimensional effect very well. Unfortunately, I'm not an artist and I'm not able to do that. You have to imagine this. This 1, 2, 3, and 1, 1, 1 are the, okay, I go back one more step. Sorry, I have to rotate this now. Okay, you see here, this 1, 2, 3, and 1, 1, 1 are the two column vectors here, right? I take the plane spanned by those and then observe that 1, 3, 3, the problem why this system does not have a solution is precisely because this 1, 3, 3 does not lie on the plane spanned by these two vectors. It sticks out. It does not lie on that plane. So this is what I have tried to depict in the next picture, which I will again now have to change. Sorry for this mess. Okay, this is the picture. So I hope. Oh my God! Sorry. So this point does not lie on this picture. Okay, you asked about accuracy. The point is, there is this point here. The tip of this red arrow here is. I mean, intuitively I claim it is clear that. I mean, this is clear when you think of three-dimensional space. There is a point on the plane that is closest to this 1, 3, 3. And it is my job to find that point, that is closest to 1, 3, 3. And once I find that point, now it is clear what is left for me to do. All I have to do is find that point accurately. Yes, there is in fact, we are going to show you. I'm going to give you a formula to find it. Okay, and once that is found, I just replace this 1, 3, 3 by that point, and then the system will have a solution, and then I can go ahead and solve it, and that will give me the line of best fit. So that is the solution to our problem. So here I have written replace 1, 3, 3 by its orthogonal projection to the plane P. By orthogonal projection, I mean you drop a perpendicular to that plane from the point 1, 3, 3. Okay, so here is the plane, and here is I've denoted this perpendicular drawn here. Drop a perpendicular from 1, 3, 3 to that plane, and replace this 1, 3, 3 by that point, this vector, the coordinates of this vector here, its projection. What we have called the orthogonal projection. It's called the orthogonal projection because I'm dropping a perpendicular from 1, 3, 3 to that plane. And that is the crucial idea. That is, I replace this 1, 3, 3, I remove this point or this vector and replace it by the coordinates of the vector P, whatever that is, and we have to find that. And there is an accurate formula which I'm going to give you, which we will talk about for finding that point. And once I find that point, I just